Thank you, Lucas Frage, for being here. He's a lead researcher in zkM. He's going to be talking to us today about proof systems, SNARKs, STARKs, and PLONKs. So with that, I'll hand it over to you.
Okay, cool. So, hey guys, my name is Lucas. I work for zkM, and today I'll be talking about SNARKs, STARKs, and PLONK. Well, SNARKs and STARKs, they started as special proof systems, but they were expanded a lot. And today we think of them more as classes of proof systems than as proof systems themselves. So what I will try to explain here are the classes, not the original proof systems, okay? So to explain the classes, I have to make some simplifications, and I leave some details like outside the presentation. Also, I have to make one very hardcore simplification to make the presentation more easy to understand, and I will let you know when I introduce the simplification, okay? And why I chose these proof systems? Because these are the proof systems that we use in zkM to design our zkVM, which is called zkMIPS. We use STARKs on the base, we use PLONK in the middle, and in the end we use a graph 16, which is a SNARK. When I was preparing this presentation, I assume that everyone is familiar with what a zk proof is, like that we have a prover, we have a verifier, we have a problem, and the prover wants to convince the verifier that it has a solution to that problem, okay? Though these proofs, they are often called zk proofs, zk is not the focus of this presentation. I want to make this very clear too. The focus here are the proof systems themselves and the differences between these proof systems and how these differences impact the features of each of them. Okay, so I'll go straight to the problem that I'll use in the proofs that I will show here. I chose the Pedersen commitment scheme. People usually use Fibonacci when they're explaining zero knowledge proofs, because Fibonacci is very simple, but Fibonacci is not really useful. So I chose something that is almost as simple, but it's more useful, which is Pedersen commitments. First of all, what is a commitment? A cryptographic commitment is a value that you create when you want to commit to another value. So we have a committed value and we have a commitment value. And the idea is that by sending a commitment value to someone, this person cannot extract the committed value from the value they received. But at the same time, you cannot change the value you committed. Once you settle the commitment value and you send it, you cannot change the original value. And this is very useful for cryptography in a number of ways. We even use it to design zk proofs, as I will show later. And Pedersen commitments, the instance, we need a large prime Q to use as our prime field. And we need two generators to this prime field, G and H, okay? And the discrete logarithm between these two generators must be unknown. So no one should know the log of H on the base G and the log of G on the base H, which are basically the same number, but this number should be kept private from the prover and from the verifier. Once these values, they are generated, we output them, and to compute a commitment, to a value x, we need a random value y to compute a commitment like this. We put the value that we want to commit to on the exponent of g, and we put the secret value that we chose. We just chose, and we will use just once on the exponent of h. And okay, now we have this commitment. We send this commitment to the other person. When we want to open this commitment to the other person, we just send x and y. Okay, very simple. How we state the knowledge of a committed message. Given the public inputs q, age, and q, g, and age, and a commitment value, we can claim the knowledge of the commitment if we can find x and y such that this equation holds. This equation is basically the same from the previous slide. I just moved the y, the h power to the other side to make clear that if we are able to find x and y just from the values that were given, we are able to solve the discrete logarithm. And this is something that we are not supposed to do unless we already know the discrete logarithm. And this is why we need to get rid of it right away. Okay. And this is the base of the security of Pedersen commitments. If the logarithm is known, the entire scheme is at risk. Okay, and how we argue about the knowledge of a message. We can just disclose x and y, and additionally sum the x and the y such that the equation in the middle holds. And this equation is very similar to the equation from the left. The only difference is that we changed the modulo. So we're not working on the prime field anymore. We are working with integers. And this might be important because we might not want to use the original field, right? We might want to work on another field. And in this case, we cannot change fields right away. We need to go from one field to the integers and then from integers to another field. And the verification is also very simple. You just receive the values and you check that the equation holds. What's public and what's private here? Q, G, H, and C are public. X and Y are private. The X and the Y are auxiliary values. Why these auxiliary values are important? The good thing about this scheme that I'm showing here is that the verifier don't have to compute the X and the Y right away, okay? If these values were not given to the verifier will have to perform a division that is very expensive, and we want to remove as much complexity from the verifier as we can. So we can help the verifier verify the division instead of performing the division. We can help it verify the division by giving these dividends to the verifier. And this makes the verification way faster, which is something that we want to. This is not exactly succinctness, but this is the base of succinctness. Succinctness is about removing complexity from the prover, from the verifier, and putting more complexity on the prover. Succinctness is about other things as well, but this is the base for succinctness. We always want a fast verification, even if it makes the proving procedure more expensive. So this is it's a good thing about this scheme that I show here. But what can be improved about it? First of all, it depends on the discrete logarithm being eliminated, deleted. This Ideally, no one should even know this discrete logarithm, but we need to trust that someone didn't compute age as a power of g, because in this case it would know the discrete logarithm. We need to trust that someone chose these values faithfully, and this is a big problem because we don't want to trust anyone. Ideally, we want to remove any source of weakness, and trust in people is a source of weakness for zk proofs, and this is something that we really don't want. Another thing that can be improved is, well, we are disclosing x and y, and this reveals knowledge, right? The prover might want to keep x and y private, and this is not the case in this protocol. This is why it is naive, okay? So we're not caring about privacy here, but this might eventually be a problem. Both the problem on the left and on the middle, they are things that we want to deal with, ideally. The problem on the left represents a lack of transparency, and the middle, lack of zero knowledge. And these two things are things that we want to ensure. Okay, so now that I defined these three properties, succinctness, transparency, and zero knowledge, we can compare SNARKs and STARKs. And basically, SNARKs are arguments of knowledge that are succinct and non-interactive. Arguments of knowledge because we are not proving the knowledge of something, we are just arguing about it. There is a chance that we don't really know the value and still we are able to convince it, but we can make the verifier as confident as he wishes that we do know the values that we're claiming to know. And this is what is called argument, not a proof. In practice, arguments are enough because we can make the verifier as confident as he wishes. SNARKs, they are succinct, they are non-interactive. Non-interactive in the sense that the verifier don't need to communicate with the prover to verify the proof, right? It might not even know the prover, might not even know who created the proof. It can verify the proof alone because the proof itself gives the verifier all the information it needs to verify. And well, STARKs, they are also arguments of knowledge. They are also non-interactive, but they're not succinct. Instead, they are scalable and transparent. And what scalability means? Scalability is basically you can prove problems of any size. Okay, SNARKs, you can prove problems up to a certain size. The size depends on a few factors that I will explain briefly, but STARKs don't depend on these factors, so we can prove problems of any size. And this is very important for blockchains because, well, we don't always know the size of the problems that we want to prove, and the problems, they are just getting bigger and bigger. So STARKs allow us to prove problems of any size without requiring any kind of trustness, and because they are also transparent, but they're not succinct. The fact that makes them scalable and transparent is the same thing that makes them succinct. Okay, so yeah, these are the differences between SNARKs and STARKs. Now I will start to explain graph 16 and the original SNARK, which are very similar. There's a class of SNARKs that look like these two protocols. PLONK, although PLONK is a SNARK, it's very different than the rest of the SNARKs. In a lot of ways, it is almost the same as SNARKs. So we can say that it came from SNARKs. SNARKs came from it, but actually PLONK arrived later. So yeah, it's in the middle between these two classes. And finally, I'll explain SNARKs. I put PLONK here because although PLONK and well, PLONK is a framework, is a library that we use in zkM to produce our proofs. And that's why I put it here. How I will explain these proof systems. I'll describe the language they use to describe the problems that we want to prove, how they synthesize this language to mathematical objects that can be verified, and how they evaluate these objects, how they verify that these objects correspond to the original problem, and to a solution to that problem. Okay, and well, what are the languages, the synthesis, and the evaluation mechanisms for each of the proof systems that I just showed? Graph16 and SNARKs, and the original SNARK, they use R1CS as their language. I'll explain what this means. They use QAP or QSP to synthesize this language. Don't ask me the difference. I never really got it. For me, they're very similar. I don't see differences at all. I don't think they should have different names. But it's something very clever, and it was state of art once. And they use a pairing test to evaluate the QAP or the QSP. PLONK uses an arithmetic circuit as its language. Then it compiles this circuit to a polynomial representation and uses a quotient test to verify whether these polynomials, they match the program and the problem and the solution. SNARK use arithmetic CPU, which is similar to arithmetic circuit, but gives us more freedom. Then it compiles this CPU representation to AIR, which is very similar to polynomial representation. It's just a bit more specific. And it evaluates the correctness of the AIR instance using a quotient test, just as PLONK, with a Frye instance. Frye helps SNARKs become transparent. It's not the only reason why SNARKs are transparent, but it's a major part of it. Without Frye, SNARKs wouldn't be transparent at all. Okay, so let's start with graph and the original SNARK. How they expressed a problem with R1CS, and what R1CS means. It means basically we are multiplying linear combinations of variables. Okay, so though in this slide we have like two variables being multiplied at a time, don't think of these equations as products of variables. Think of it as products of linear combinations. So for instance, the first equation, it is 1 times g squared plus 0 times the rest of the variables. This linear combination is equal to 1 times g plus 0 times the rest of the variables, one linear combination, times another linear combination, which is 1 times g plus 0 times the rest of the variables. So when we're talking about R1CS, it's important to think of it as linear combinations, not as variables. The variables, they have a less important meaning here, okay? So yeah, this is how we compute the power, this power of G and this power of H. And this is the disclaimer that I made in the first slide. We cannot do this in practice. If we want, if we're targeting zero knowledge, we cannot compute the exponent of a number this way, because even if we made this protocol, zk, it will leak a lot of information. The number of equations that we have here reveal x and y, for instance. So we cannot do this in practice. If we really want the proof to be private, if we really want zero knowledge, we need to use an algorithm called square multiply. I didn't want to put square multiply here because it would make the presentation more complicated, and it will make it would add a lot of variables. So I made this simplification, but this is something that we cannot do in practice. Please don't do this. This is just to make it simple to understand, okay? If anyone is interested in how this should be implemented in practice, we can discuss this later. Okay, now the second half of the R1CS. We continue to have linear combinations. The first equation is a linear combination, trivial linear combinations, right? So we just have one in Q dx on the left, and then we have one on Q and one on the X on the right side. The second equation, things start to get interesting, because now we have a real linear combination. We have left trivial, and on the right we have one, which is a linear combination. We have a constant 1. We can have a value that is a constant. So it's 1 times 1, a linear combination. And the second parenthesis, it's 1 times gx plus minus 1 times q dx. Okay. On the right side, in orange, we have 1 times ch minus y plus minus 1 times q dy. Okay, so this is why it is very important to think of all these constraints as linear combinations. And how we synthesize these linear combinations, these R1CS, to something mathematical that can be verified very fast. We will transform the coefficients of these linear combinations into matrices. And this is why it's so important to use linear combinations here. Well, here you can see that we have 3 matrices, right? The first matrix, it shows the coefficients of the values on the left side of these equations. So here, linear combination is 1 times g squared plus 0 times the rest. This gives us the left linear combination on the right. So 1 times g plus 0 times the rest. Well, let's go to the second report, actually. It's more interesting. 1 times g, 0 times the x, the rest. 1 times g squared, 0 times the rest. Okay, so these encode these constant values, and this encode this here. We do the same with the powers of h. And here, the more interesting example, this is a simple product of linear combinations. Here we have this linear combination, and this is why we should think of it as linear combinations, okay? Because we can put the coefficients here, and this represents the sum of this value times this one, this times this one, which is exactly what we are capturing here. And well, you can see that we do the same in this row and the same in this row here. And why we represent this as matrices? Because we will represent the solution as a product between matrices and vectors. Now I will clean a little bit the notation, because it's very important that all matrices have the same set of columns and the same set of rows. So they must all have the same size, and it just wouldn't fit the screen. So I made this cleaner example here. These A values, they continue to be coefficients from the R1CS. But now we are multiplying this matrix of coefficients by this vector of solutions. So this value here is the value that this variable should take. This value is the value that this variable should take. So when we are multiplying this matrix by this vector, basically we are doing this. Okay, so this is Math 101, multiplying matrices and vectors. We can see that each column will be multiplied by the same value. Okay, and this is useful for us because we can make a better encoding of this linear the coefficients of the linear combination. So we can, for instance, encode all these coefficients here as evaluations of one polynomial. So we are encoding this column as a polynomial. And how we do this? We will define a polynomial A1 such that the evaluation at 1 of this polynomial A1 is equal to this A1 from before. Okay? And we do this with every value from every row and every column. So now we have vectors, the rows, and we have polynomials for the columns. And we can go further. We can also have polynomials for the rows. How we do this? We will define this polynomial A such that when it is evaluated, for instance, at 1, it will give the sum of the first row. And how this is done? We have a sum of the polynomials of all columns here. They are all being evaluated at the first position because it's the first row, and each polynomial is multiplied by the respective variable. So this way, if we want to verify the value of the first row, we put 1 here in this I, and we will have A1 is equal to A1 times X1, A2 1 times X2, A3 1 times X3, and we get the sum of the entire row. This is how QAP and QSP works. And now we have one polynomial that is encoding the entire matrix for us. And we can do the same thing for the other matrices from the R1CS. So say that we have, now we have matrices A, B, and C encoding the left variables from the R1CS, the variables from the linear combination on the left side of the equations from the R1CS, the first linear combination on the right and the second linear combination on the right. And to evaluate the entire system, we can define this polynomial P, because if A is equal to B times C, then A minus B times C should be equal to 0. So what we are doing here is we are defining a polynomial P that will be equal to 0 if and only if A is equal to B times C. And well, this is how we transform that huge system, that huge R1CS system, into one single polynomial that will be equal to 0 if the entire system is correct for a given solution, okay? And how we test the correctness of this system using this polynomial P. Well, we have to evaluate this polynomial P together with A, B, and C on unknown values using a special vector of elements chosen by a trusted party. And this is why Graph16 and SNARKs in general are not transparent, because we need a vector of values that is chosen by a trusted party. So we need to trust that this party deleted these values, okay? Because no one should know these values. We should just know values that are related to them, but we cannot know the private values, because otherwise the security is at risk. Okay, so yeah, we have this special vector that we call a setup. We actually need two setups. Okay, we need this vector for two different secret elements, and we will evaluate the polynomials twice. One for each of these unknown values. And we, doing this, we can ensure, actually it's the prover. We can ensure the prover composed polynomial equations using the third-party setup. Why? Because we don't know the secret value, and we cannot produce these polynomial evaluations without using this setup, right? So this is the first thing that we convince to verify of. And well, this the setups, they are correlated in a way that allows polynomial evaluations to be verified using a pairing function. Pairing functions are very heavy crypto. They're not, well, understanding them is not that difficult, but their implementation is, and they have a lot of properties that we use in the verification. That's why I don't describe them better here. But pairing functions, they need a lot of things to work. And when they do work, like if we have a proper environment with proper variables for them to work, they allow us to evaluate the polynomial properties that we want in a way that is very succinct. We need to give to the verifier very few elements to convince him that we compose the proof, the argument correctly. And well, basically, this is what ensures Graph16 and SNARKs in general properties, right? The evaluation of polynomials on unknown values and the use of pairing functions to check the relation between these polynomials. This is what makes SNARKs succinct, but it's also because, well, we have to compute few values and send these values to the verifier. So it's very fast. No, not very fast, it's very small. And the size is constant. So no matter the size of the problem we want to prove, we can prove it with, I don't know, 7 or 9 elements. I'm not sure. So it's succinct. It's not transparent because we need a trusted setup, and it's also not scalable because we need a trusted setup, and the trusted setup allow us to prove problems up to a certain size. Okay, so this is Graph and the original SNARK, and now I'll go to another SNARK that is PLONK. And well, the beginning of PLONK, it's very similar, okay? This slide is the same, actually, as graph, but now we shouldn't think about these equations as products of linear combinations. We should think of them as products of variables, okay? And we might also have addition here. We don't need to have multiplication always. So now, basically, the difference from graph to PLONK is that we are not talking about linear combinations anymore. So we're not talking about matrices. We are talking about variables, okay? This slide is the same. The second slide is a bit different. The first equation will be the same, but just multiplying these two values that were linear combinations before, but now are just values. Then on this third equation here, we are adding them, okay? We are adding the value that we computed before with the value that we are computing here. And why I didn't put it right away here on this line? Because the original version of PLONK and a lot of versions actually just support addition and multiplication and other simple operations, but we don't have to support subtraction to compute subtraction. We can compute the inverse of a value this way. Okay, we define a new variable that, when added to the original one, is equal to 0. This means that this is equal to minus this one, and this can be used to perform a subtraction. The same happens here. We are multiplying two elements here, multiplying two elements, inverting one, multiplying, adding 2. Then we invert this one that we computed, and here we sum these two variables. That's arithmetic circuits. And now how we synthesize this language to something that can be verified. We are not talking about linear combinations anymore, so we don't use matrices. We use variables, right? And here comes the abstraction of a circuit. We have, for each equation from before, we have two inputs and we have one output, which resembles a gate, okay? So here we will represent all our gates will have one output and two inputs. And we just need three variables to represent the inputs and outputs for all equations, okay? And this is what's being done here. As before, we will represent these columns of this table. This is not a matrix, this is a table. We will represent the columns of this table as polynomials, right? And now we need to represent the operation that will be performed in each of these rows. And to do it, we need new columns to represent these to represent these operations. Here we are just using multiplication, so this entire column is 1 and this addition column is all 0. We call this selection. These are selector polynomials, and they are polynomials because we will encode these columns as polynomials. Okay, so now that we have these 5 polynomials, we can represent what's going on in each of these rows. We will define we will represent these equations here as this polynomial equation. This means that the value on the first column should be equal to the sum of the second and the third column if the fourth column is equal to 1, or should be equal to the product of the second and third column if the last column is 1. Okay, so this is why we call these columns selectors, because they select whether this column will be equal to the sum of these two or the multiplication of these two. And well, now we need to ensure a few more things here, because we don't have one variable for each value anymore. Now we will put more values inside the same variables, right? So here, like this variable has this value here, but on the other row it has this other value. So we need to tie a little bit these values. The first thing we need to do, we can do to ensure this, is creating input constraints. These input constraints, they let us verify that certain variables will have values that were input to the protocol. And we do this for these variables because these two first variables, they should be equal to the first generator, and the last variable should be equal to the second generator, and the third variable should be equal to the constant one. We should also verify that copies were made properly. So we can create copy constraints that will be compiled to polynomials. Okay, the input constraints, they are compiled to polynomials as well. And everything is polynomial here, all constraints. The copy constraints, they will ensure that the certain values from this table are equal to others. And we do this with this column, and we should also do this with the outputs, because we have to move the output from one row to an input of the next row. So this is how we do it. We need to create copy constraints to ensure this. And finally, we can define all these constraints as polynomials that will evaluate to 0 if the desired properties hold. Okay, so all polynomials should look like this. They should be equal to 0 if the property is correct. And to prove that all these properties hold, we should prove that these polynomials are equal to 0. And we can prove that all polynomials are equal to 0 at the same time if we define a combination polynomial. How the combination polynomial looks. It will be the sum of the difference from the equation that we had on the table. Okay, this should be a minus, I guess, right? This first line shows that this polynomial is equal to this one plus this one, so this should be a minus, because all of this should be equal to 0. And then we will multiply each other constraint by a value that is different than 0. Why we do it like this? Because this ensures that if this constraint is equal to 0 when evaluated at x, then alpha times this constraint is also equal to 0. If it's not equal to 0, then alpha times this constant is not equal to 0. So alpha kind of amplifies the value and also randomize it, because this alpha should be chosen by the prover in a random way, and this random way can be verified by the verifier. There are techniques to do this. And by multiplying each constraint by a value that is different than 0, we can be sure, we cannot be sure, we can believe it with high probability of being true, that this will be equal to 0 only if this is equal to 0 and each other constraint is also equal to 0. So yeah, this is why the combination polynomial is designed like this. And now to prove the combination polynomial evaluate to 0 at all values, we should give to the verifier a quotient polynomial Q such that this equation holds. What this equation says to us. The polynomial z is equal to 0 in all positions that we want to test. So if there exists this Q such that this equation holds, it means that c is also equal to 0 in all positions, right? Because this polynomial is equal to 0. So if this is equal to 0, this is equal to 0. We are basically removing the zeros from this polynomial and disclosing the remainder of this operation. Not the remainder, the quotient of this operation, right? Because the remainder should be 0. And well, this is enough to show that this combination polynomial is equal to 0, but how we can evaluate this in a way that is fast and that is zero knowledge compatible. We will use a commitment scheme called KeysAG that is not transparent, okay, but it's very efficient. Because KeysAG is efficient, PLONK is succinct. Because it's not transparent, PLONK is not transparent. And it's not transparent for the same reasons Graph 16 is not transparent, because KeysAG requires a trusted setup. And it's not scalable as well for the same reasons, because the trusted setup allows us to produce proofs for problems up to a certain size. And we cannot produce larger proofs for larger problems unless we redo the trusted setup procedure. And while KeysAG is very similar with what happens in Graph 16, just came after it, and has a bit more features. So, but the reasons why it has the same properties are also the same. So this covers PLONK, and now we can go finally to STARK. Well, the language that STARK use is an arithmetic CPU. It's very similar to what PLONK does, but the difference between an arithmetic circuit and a CPU is that the CPU gives us more freedom in the polynomials that we compose. It doesn't give us like all the freedom we want, because the degrees of these polynomials should be restricted, but we can like have polynomials of any degree we want if we make some modifications in this language. But anyway, here you don't have to think of these operations as gates that have 2 inputs. We can have as many inputs as we want. And we are not restricted to just additions and multiplications. We can combine them in any way we want. We can multiply something by we can multiply a variable by another variable or by a constant. We are free to do whatever we want, as long as we keep the degree of the polynomial small. And this page is very similar to Graph and PLONK, but this one, it's very different. You can see that we don't need to perform a multiplication in one equation, and then inversion, and then an addition, as we did with PLONK. We can do all of this. We can do all of these at once in this polynomial, and the same on the other side. Okay, we just need to compute these powers before. So we compute them as in the previous slide, and once they're computed, we can play with these variables as we wish. And why this is cool? Because these more complex polynomials allow us to reduce the size of the columns, the height of the table. And this is how it happens. Suppose that we have, for instance, 6 columns available to us. And because now we're talking about an arithmetic CPU, I'll call this columns registers. If we have 6 registers, then we can fit the exponentiation of G and of H on the same rows, okay, one at a time. So for instance, here we put G squared, and G in these 3 polynomials, in these 3 registers. Actually, this one don't even need to be here, right? Because when we access it, we just access the value on the first register and the value on the second register. We don't have to deal with the register. Here, the same, we access these and this register. We don't have to put a 1 here because we can put constants as we wish in these polynomials. And we can do this until we get gx and h minus y. But the interesting thing happens in this last row, because even though here we have more than 3 variables in each of these equations, we are still able to fit 2 equations on the same row. Why? Because this way, with R, we can access values that are in other rows. So here we have left in this row, Q in this row, dx in this row. But we can also access gx from the previous row if instead of using r0x, we use r0x minus 1 to access the previous row, okay? And this allows us to fit very complicated polynomials in the same row and evaluate them together, and by consequence reduce the number of rows that we need in these columns. And here we can even model this equation here on the same row. We can put 3 equations on the same row, because all this needs is left and right, and left and right have already been computed here. So we can just access these values and see if they match. And that's it. That's R. That's why R is in a certain way more compact than the polynomial representation from PLONK. And this is enabled by the way that that the arithmetic CPU give us more freedom than the arithmetic circuit. Okay, how these constraints are evaluated? We might have to use copy constraints or input constraints here. We are allowed to use them, no problem. We will join all these, we will combine all these polynomials into one combination polynomial, right, as before, as PLONK. And we will test that this polynomial is equal to 0 in all positions using the quotient test as PLONK. However, this is not enough, because now comes transparency. To make this protocol transparent, Stark uses Merkle trees instead of keys AG. And Merkle trees, the good thing about them is that they are transparent, right? We don't need any value to create any secret value to create a Merkle tree. We just need a hash function. And with a hash function that is public and that everyone trusts, so we don't have a trust issue here. Anyone can compose a Merkle tree and can compose a Merkle tree of any size. So besides being transparent, it's also scalable. But Merkle trees are very inefficient because the prover have to compute a lot of hash functions and the verifier has to verify those hash functions. And both these operations take a lot of time and they depend on the size of the columns. So this is why Starks are not succinct. And well, how we create this Merkle tree? We will put in each Merkle leaf a polynomial evaluation, and the number of polynomial evaluations should be larger than the columns. We need to do this if we want to enable zero knowledge. I don't have time to explain how, but trust me, we need to commit to a domain that is larger than the column, than the number of columns, if we want to enable zk. And the number of columns should be a power of 2 to enable Frye. Okay, so if it's not a power of 2, we must add it with empty rows until we get a power of 2. And the factor between the domain that we commit to and the number of rows, the size of the columns, should also be a power of 2 in order to Frye, in order to enable Frye. Okay, and what Frye does? Frye will show us that this larger domain, which because it is larger, it might represent a function that is not polynomial, so we can change the values that we want to commit. We could change the values that we commit to as we wish if we didn't have to run Frye later. Frye help us verify that the function that was committed to in the Merkle tree behaves like a polynomial of the same degree as the number of rows, the size of the columns. And this is what Frye does. Without Frye, it would be very easy to cheat on this phase of the protocol. We could commit to the values that we want in the Merkle tree and the verifier wouldn't notice. But if we run Frye, we can be sure that the values that were committed, they could be put into a column of that size. And this is what gives us the properties that we want to argue, okay? So yeah, this finishes Starks. This is why, well, the Merkle tree is the reason why Starks are transparent and succinct, but they're not efficient. They're not, they are transparent and scalable, but they're not succinct. And Frye is the reason why Stark is our argument, because otherwise it wouldn't argue about the solution at all. And well, I put this table here just to review it very quickly after the presentation, but I don't think we have time. So I just leave it here and take any questions if you guys have any.
All right, thank you. I think, yeah, we have a few minutes. If anyone has questions that you want to go ahead and drop in the chat. I think a couple might have come through while you were just talking there. If you want to take a look at those, or if you want to elaborate on what you said there.
Yeah, well, I think the first one was more about, I think it was about PLONK, where where we showed, no, was it, what, it's probably, yeah, I can't remember, it was for the PLONK, where you showed how you are calculating the polynomials for each constraint. You know, you had a summation equation there at the bottom. So the question was, does every constraint, for that matter, adds up to the number of polynomials, the increased number of polynomials?
Here,
No, it was the another one where you had a summation equation at the bottom.
oh, okay. So it was growth, I think.
Yeah.
It was yes, it was Q.
You had the A, yes, this one and the next one, where you had an uppercase A, yeah. Yeah,
Here?
so, yes.
So you want, what exactly you want to know?
So basically, so you have like 6 constraints here, right? And you have these polynomial calculation, A1, 1, A2, 1. Does this mean that every constraint adds and calculates a new polynomial for that point?
No. No, because the different x, they are constant. Okay, they are part of the solution. So they are values that the prover chose. So we are multiplying each of these polynomials by a constant value. This change the degree of the polynomial. Now we are adding many polynomials, okay? But all these polynomials, they have the same degree. They have degree 6 because they're encoding 6 values. When we add polynomials with the same degree, the degree doesn't change. The degree of a sum of polynomials will be equal to the maximum degree of those polynomials.
Okay.
It makes sense?
Yeah, it doesn't mean here that the degree of the polynomial is equal to the number of constraints, right? Just to make sure that I'm not confused.
No, it is. It is.
Oh,
It is equal to the number of constraints.
I see, okay.
But each polynomial is degree 6. So when we add all degree 6 polynomials, we get a degree 6 polynomial.
Right, okay.
Or smaller, actually. We could have like a degree 5 if the coefficients of x to the power of 6 cancel each other, but don't count on this.
Okay, thanks.
You're welcome. You had another question for SNARKs. Does each leaf spin?
Yeah, and it's, you know, I'm not a SNARK expert, but it just felt like the one point there about why the verification time is more, and every leaf contains some part that needs to be verified in the Merkle tree. Is kind of an obvious question. Why don't we just verify the root instead of, you know, all the leaves?
Okay, so we need the leaves, and we need to open the Merkle paths to get the values that are on the leaves. We need to do this as part of the Frye protocol. And you know something about the Frye protocol?
Yeah, just very little, not the mathematical aspect of it.
Okay, so it's, well, what Frye does is it has a big domain at first, right? And it will divide this domain in half in each iteration. And it will divide this the size of this domain doing some very clever polynomial evaluations. And there's a formula for this. I can send you later if you want. You can DM me on Telegram. Don't DM me on Twitter because I don't have Twitter right now.
Okay.
Because I'm from Brazil. anyway, you have this equation, and you use it to divide the side of the domains that you have. And to do it, you have to query some values from the polynomial, and that's why you need to open the Merkle tree, right? The Merkle. The problem is that these polynomial, these values that we query, they are random. So you cannot know beforehand which values you have to query. So you have to compute all values, because you have to query some of them, but you need to be able to open any of them.
Right. So that happens in the querying phase of the Frage,
Yes.
right? Okay, where the verifier has to check sort of like the collinearity of the requirement to fulfill that.
Yeah,
I see. Yeah.
This procedure that breaks the size of the domains, it is random, and exactly this randomness is what requires us to commit to the entire domain.
Right. Makes sense. Thank you.
You're welcome. Okay, in graph 16, does the verifier do the pairing test on the second, meaning it operates on the points of the second curve and has nothing to do with it? It's actually it's the same curve. So pairing functions that I mentioned in graph 16, they operate over elliptic curves, and that's the complicated part of it. And they are functions that receive two values from two different groups inside this elliptic curve. So you have an elliptic curve, which is a group, and you have two subgroups of it that are generated by the two generators. And the pairing function, the pairing function, it will verify properties between these two groups that are on the same elliptic curve. That's why we need two setups on graph. We need two vectors for two different secret values, because the pairing function, it receives a pair of values, right? So we need these two groups, but they are groups of the same elliptic curve. Yeah, it's confusing, but like elliptic curve is a big group, and you operate over smaller groups of this elliptic curve, but they're all inside the same universe. I'd like to know why it is mentioned. The polynomial must be of low degree. I don't understand this question, Emmanuel. Let me go back to.
Well, I just opened up the microphone, so Emmanuel, if you want to talk, you could. If you unmute yourself.
Well, someone asked if it's different group order. I don't think it's a different group order. I'm not sure. I think it's the same group order, but different groups. Different subgroups of the elliptic curve.
Right. Okay, just quick before we end. I mean, I just opened up the microphone, so if anyone wants to unmute and ask a final question. Otherwise, it's up over to you, Sarah.
All right. Yeah, if there's no other questions, I think we can go ahead and wrap up for today. Lucas, thank you so much.
You're welcome.
Anyone that thinks of any other questions afterwards, feel free to put them in Discord, and somebody from the team will get back to you. Otherwise, thanks for joining, and we'll see you tomorrow.
Okay, bye guys. Have a nice day.
Bye. Thanks, Lucas. Bye, everybody.